Ni hao. Hello. This is the 14th lesson in heat transfer. In this lesson, we will be discussing transient, one-dimensional conduction heat transfer. In prior lessons, we had been looking at steady-state, multi-dimensional conduction heat transfer. And prior to these lessons, steady-state, one-dimensional conduction heat transfer. We now continue our series of lessons on conduction heat transfer, but now the problems will be transient. We'll thus be asking how long questions. You may wish to review the lesson video that discusses the difference between transient heat transfer, steady-state heat transfer, and unsteady heat transfer. In the first part of lesson 14, we will look at an example problem, and we will derive the governing differential equation for problems of this type. By the end of this lesson, you should be able to provide one example of an engineering problem that fits into the category of transient, one-dimensional conduction heat transfer. You should also be able to identify the governing partial differential equation for problems of this type. On with the lesson.
But we also have lots of situations in which we have transients in heat transfer with temperature gradients. And to show you where you might see that, can show you, we're going to go back to the steel processing facility. So when they go to pour this molten steel into the molds, right? Find it. They come out right around here. So they're about to pour the molten steel into molds and through dies. And what is going to come out of these molds are the beginnings of a steel bar. So right here at this moment, right? Do you see these are like long, really hot, just barely solidified kind of steel bars, and they look rectangular almost if we were to be able to get up and look down on top of them. So this is after the molten steel has been poured, but now these bars are going to go onto these rollers, you see, and they're going to roll down a line, and we're going to manipulate them to kind of tune the properties of the steel. But if you can imagine now, as they're rolling down the lines before they go to the next step, and maybe they're going to go to a quenching step next, or maybe they're going to go and be cooled and then reheated for an annealing process. But they're cooling right now, right? Like this red hot steel bar, it is being cooled in this ambient environment. There is convection on its surfaces, and there's also radiation. And understanding, right, the temperature variation across the thickness of the bar would potentially be important. And if you check the BO number for bars of this thickness, you're going to find that the BO number is not less than 0.1. So there are actually going to be gradients in temperature between the surface of this bar and the center line of the bar. And if we had some desired temperature that we either couldn't drop below, or when we go to anneal the bar, we want to, Daniel says those would probably be white if you were, yeah, they might look white. Yeah, it depends on, yeah, exactly, that the sensitivity of the camera to the different wavelengths that are being emitted from that super hot bar. But we want to be able to predict, right, what's happening in time with the temperature and account for the fact that there could be gradients in temperature along the thickness. And that's because there is either conduction, right, that is resisting the heat transfer out of the bar, or if we're thinking about heating it up, there'll be conduction that resists the transfer of energy from the surface of the bar into its center line. So that would bring us to essentially transients with 1D temperature gradient, right? If we imagine that the bars are very long and we're only going to focus on variations in the direction above and beyond above the bar and into the center line, we could take that steel bar, right, and turn it into what looks like a plane wall for us. So if you imagine then what I've drawn here as taking that bar coming off of the hot line, right, and turning it up on its vertical. So we're looking at it vertically and kind of looking from the edge again. All right, what's happening here is there is some we're going to say there's some convection, right, that's happening on both sides of the bar. And based on that picture that I showed you, it looks similar, right? Like the convection is going to be similar. So on both sides of the hot bar, we have some convection, and it's characterized by the same convection coefficient and the same ambient temperature. We're going to define our x, right, from the line that goes right through the center of the steel sheet. And hopefully you see that the problem is symmetric, right? It looks the same on the right half of the bar as it does on the left half of the bar. So this is a line of symmetry. So if you imagine, right, and you think about what the temperature profile might look like in the slab, whatever it looks like, if we're, say, trying to cool it down, right, it might look something like this, where it has the highest temperature on the inside and it cools down to the outside, to the surface of the bar. But what's important with the symmetry is that at the middle, right here, the slope of this line is what?
Zero.
It's 0, okay? So that means dt, right, dx is equal to 0 right here. Agreed? So if dt dx is equal to 0, what's true about the conductive heat transfer flux at x equals 0?
Now, what I would like you to do is pause the video and write down an answer to the question.
Is it 0?
It's got to be 0, yeah, because conduction is governed by Fourier's law, right? And so it's minus k dt dx at that location. If the gradient's 0, there is no heat transfer across the symmetry line. This is always true, okay? In any problem that you ever encounter, if you see a line of symmetry in the heat transfer problem and it's a conduction problem, there is no heat transfer there. So this is going to be a really handy boundary condition for us when we go to solve this problem. We can use that to our advantage, right? So even though there is heat transfer in the bar, right, it's got to be emanating from the center and moving towards the surfaces symmetrically on both sides, so that there is no actual transfer of energy across the symmetry line. No net transfer of energy. Does that make sense, what I just said? It's kind of important that you're able to see that. Okay, so lines of symmetry are our best friend in heat transfer because they simplify problems down. Okay, so I'm going to erase that now. And we're going to, because of that, we're going to think about the thickness of the slab as being 2L thick, right? And we have some, you know, initially inside of the slab, if I look at some little chunk, right, and I were to ask myself, what's the temperature, right, at this particular location X at T equals 0, right? So I'm looking at the temperature at some position X, but initially, right, before the heating or cooling has happened, we're going to say that the temperature everywhere, right, is equal to just some initial condition Ti. So initially the bar is going to have a flat temperature profile, and we're either going to heat it up from that or cool it down from that flat temperature profile. And we want to see what's happening in time. So this is called our initial condition. And then we have already talked about our two boundary conditions, right, which I'll write down now. We just said at x equals 0, right? This is at all time. at all time t at x equals 0, the gradient is going to be equal to 0, right? And at x equal L, we have our convection boundary conditions. So we have minus k dt dx at x equal L is equal to h times t at x equal L minus t infinity. So those are our boundary conditions now, and our initial condition, I'd call it I sub c, right? We're going to have all of those. So we quickly could, all right, this is a differential, we have to do the differential analysis, right? So the thermal circuit's not going to work for us because we have a storage term. This is not steady state anymore. So we really need to do our differential analysis here. So cut a little slice out of the bar, and I think it might be helpful to do it. So if I imagine cutting a little piece from somewhere in the bar, it's really tiny, okay? So it has some thickness dx, right? And it has some face area A, right? So if I imagine looking down, right, I can see the face of the steel slab. Right, I want to just redraw that quick over here. So I'm just redrawing it over here a little bigger. So this is dx this way. And this is a great review if you had a little bit of trouble with the differential analysis on the exam. And when I think about the heat transfer in here, I have some, right, heat transfer going from where I've drawn the slab from right to left. I should have drawn it in the positive x. I want to think in terms of positive x. So imagine taking this and just moving it over here, right? Then the heat transfers from left to right. So I have some conduction that goes in on the left face, and I have some conduction that comes out on the right face. And I have now also some storage on the inside because this thing is not steady state anymore. I apply the same heat transfer energy balance equation, right? So we have E dot stored is equal to E dot in minus E dot out plus E dot gen, right? There is no generation, right? I have my storage term, so I'm always putting in rho v c dt dt for the storage term. Here, just as a reminder that this is a little tiny differential slice, instead of just putting in v, I put in this dv, and all it is a reminder that it's a little tiny slice. It's a little sliver. It's not a big extent. It's not the total volume of the slab. It's the volume of this little tiny slice of cheese that I've sliced off of the slab, okay? And then on the in and the out, I have exactly what I had, right, before from when we did this way back and looked at the submarine wall, right? So you can go back and look, right? All right. This is, the right-hand side looks identical to when we did this for a steady state problem. Agreed? Does anybody feel differently? So the right-hand side is identical to the steady state analysis. So if we go and apply all of our steps, we apply the Taylor series expansion, we substitute in Fourier's law, we're going to come to the same place. Everybody agree with me on that? We're just doing a little quick differential analysis, and I'm screaming on that part because we've seen it before. So we're going to end up with a minus, all right, d dx. We will have substituted in Fourier's law, and we would have had a dx. So this outer derivative comes from the application of the Taylor series expansion, and this inner stuff comes from the Fourier's law inside the parentheses. Okay, now the little differential volume, if it has a face area A, right, and it has a thickness dx, then that volume is equal to A dx, right? I'm taking the face area and I'm sweeping it out over the length dx. So if I make that substitution, right, for my volume, and I pull out the K and the A because they're constants and they can come out of the derivative, you see that I have an A in both sides of the equation and I have a dx in both sides of the equation. And so in the end, right, our governing equation is rho c dt dt is equal to k d squared d dx squared. And a lot of times what's done is we put the derivative by it, the time derivative by itself, So we put the time derivative by itself is k over rho c times the partial of t with respect to x squared. And this collection of variables, k over rho c, is given a new name, okay? So we're going to end up, what you'll see in your book is 1 over alpha times d squared t dx squared. So this is our governing differential equation. It's a partial differential equation because we have two independent variables. We have time and position x. So it's not an ordinary differential equation anymore because we have two independent variables. We have a single derivative on time, which is why we need the initial condition, and we have a second derivative on position, which is why we have two boundary conditions. Okay, so this thermal diffusivity, this alpha, yeah, I just said it. It's called the thermal diffusivity. And it's a function of the diffusivity. It's a function of the material only. It has the thermal conductivity of the material and its density and specific heat, right? And by definition, it is equal to k over rho c. Whoops. Sorry, I put this on the wrong term. It's not 1 over, it's just alpha. Boom, sorry, not 1 over alpha, it's just alpha. So by definition, it's k over rho times c. And it's a parameter that's going to essentially tell you how quickly the energy is going to get in or get out. So the higher the thermal diffusivity, the faster the temperatures are going to smooth out and come to a new equilibrium, right? It's a balance of both the conductivity, which is how fast it's happening, and the storage of the material, which is the specific heat. So how much energy do I have to move to get the temperature to change? And the higher the diffusivity is, the more rapidly the temperatures are going to change in any location, either because there's a low capacity or there's a high thermal conductivity, or both.